Welcome back, everybody, to another exciting day of physics notes. So, what we're doing today is we're going to try something a little bit different. You should be in groups, maybe one person, probably with the bigger classes, it's going to be 2 or even 3 people per group. We're going to try to get through number 22 on the notes. Now, this is going to be for a grade, and I'm going to pick it up from you guys, or at least I'm going to come by and check it when I see you again on, let's see here, today's Monday, so I'll see you again on Wednesday. So, 1 through 22 on your notes is homework, and it is for a grade. So don't forget to get that done. You already did your test analysis with the sub, so you have a rough idea of how the forces test went. Overall, it was better than the projectiles test. Maybe not as good as it could be, but it was a big improvement, so I'm happy with that. And you should have taken your DCA. That was the 10-question quiz you just took. Remember, a good grade on that can replace your lowest quiz score, so that's pretty nice. What we're going to do in this little section right here is we're going to talk some about circular motion. I'm going to show you the concept check, although we're not going to get to it today. And we're also not going to do these practice problems today. So really just the circular motion and the concept check that we're going to look at. There will probably be a quiz at the end of next class. Not the beginning, but the end. So make sure you got your 1 through 22 done for homework, because otherwise you may be in a little bit of trouble if you haven't looked at it at all. Here is our concept check preview. Again, we're not going to get to this today. This diagram shows an object with a mass of, let's see here, 1 kilogram attached to a string 0.5 meters long. It's going in a circle with a constant speed. And we're trying to find what's called the centripetal force, which is a new term for us. We know force, but centripetal is a new vocabulary word for us. We're going to learn in this unit. Here's another one, and again, this one has something going in a circle. So this unit is about circles, circular motion. Until now, everything's been going in a straight line, and now we're going to talk about how things behave when they curve. Like when you drive your car around a curve, or when a ball is swung at the end of a string. All right, here's another one. We got a 3 kilogram mass. So we've got a mass right here. It's traveling in a circle of 0.2 meters radius, so radius is going to be important. And we've got a speed of 2 meters a second, and we want to know centripetal acceleration. So again, centripetal, and it's describing something else. And finally, a bucket of water with a rope attached is swung in a circular motion above a person's head. As you know, you can do this and the water doesn't come out. If you cut the rope right there, we want to know what the path of the bucket will be as it travels from this position. And some of you guys can probably mention, or probably answer this, based on what we know from our previous lectures with inertia. Okay, starting off, a blast from the past. We're talking about circles a lot in this unit, so that means we've got to be familiar with how circles behave. How do you calculate the circumference of a circle? Remember, that's the outside distance. Well, the answer to that question is circumference equals 2 times pi times r. So there's your answer to number 1 right there, 2 pi r. Yes, I know that diameter times pi is also circumference, and that's true, but we're really going to focus a lot on radius in this unit, so we're going to use the 2 pi r formula instead. For number 2, what happens to the circumference as the radius increases? So as radius goes up, what happens to our circumference? You should be able to guess that as radius goes up, circumference is also going to go up. It increases. If you make r bigger, c is going to get bigger too. That's that direct relationship. So the bigger the radius, the bigger the circumference, the bigger the distance around the circle. We can see that in this picture right here. So this woman is swinging in a circle around a gymnastics bar, and the question is, which travels further, her head or her feet? Here's her head moving in a circle around the bar. Here's her feet moving in a circle around the bar. And it's pretty clear that the circle made by her feet has a much bigger circumference than the circle made by her head. And that's because of the difference in the radius out from the bar right here. The bigger the radius, the bigger the circumference of the circle, the farther distance that something travels. Now, since her whole body goes around this circle in 1 unit of time, let's call it 1 second, that means her feet are actually traveling a lot faster than her head, even though everything's connected in one piece, because they travel a further distance around the circle in the same amount of time. So this question is similar. Which is going to go faster? A horse near the outside of a merry-go-round, like say this one, or a horse near the inside, like this one? And the answer is the horse by the outside is going to go faster, even though they're all connected. Because if we've got a merry-go-round like this, and we got two horses, a horse here and a horse here, well, this has a distance of about that much from the center. So it's going to make a circumference like that as it travels around. The other horse has a radius all the way out to there. So its circumference is the whole thing. And they're both going to go around in the same amount of time. So even though they're connected to each other, the outside horse moves a lot faster than the inside horse. So in this unit, not today, but in this unit, we're going to have to learn a new way to describe speed, because this is getting a little bit weird. So, how can you have a constant speed without having a constant velocity? This is a flashback to our definitions of speed and velocity. Now, velocity is a vector, right? It has both number or magnitude and direction. So the way you can have a constant speed without having a constant velocity is you can turn. Because if you turn, you're changing your direction, which is part of the overall vector. The number may stay the same. You can go 5 meters a second the whole time and never have your number change. But if you're turning, then your direction is changing. And if your direction is changing, your velocity is changing. Now, if there is a change in velocity, then what must be true about the acceleration? What must be true is that acceleration exists. It's not zero. There is an acceleration to the object. Because remember, acceleration is just defined as a change in velocity. So if turning changes your velocity by changing the direction, then technically that's an acceleration. Here's a big key point. Dun 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 about this whole thing. What I want you to remember is if you are turning, you are accelerating. Turning is accelerating, even if the number doesn't change. So write that down in your notes somewhere if you think you're going to forget that. Pause right here and write that down. Turning is accelerating. Now, this is not number 6 yet. We're going to get to number 6 in just a second. I'm just setting the stage for it. Remember Newton's second law of motion. We just learned that. F equals ma. That says that acceleration and force are linked to each other. Now, we just learned that when something's going in a circle, you're turning, there is an acceleration. So if there is an acceleration, that means there is a force. Constantly. This is a little different from linear motion. In linear motion, if you throw something into the air and there's no gravity or anything like that, it's just going to keep on going forever until it hits something. This is not true if you're turning, because turning is an acceleration. So if you're constantly turning, you're constantly accelerating, you're constantly needing that force. This is the second thing, bum, 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 I want you to take away from this lecture. The first thing was the idea that turning is accelerating. The second thing is turning requires a constantly applied force. You can't let go, you can't stop. Here we got Mr. Bruce Lee. If he's spinning those nunchucks around in circles, doing his kung fu magic, eventually if you were to cut that string, would the nunchucks keep spinning? No, one of them would fly off screen somewhere like that. Because when you cut the nunchucks, that string no longer is supplying a tension. There's no longer any force there. So things stop turning at that point. You've got to have a force or you can't have that nice circular motion. Same can be thought of if we think of Newton's first law of motion. And no, we're not on number 6 yet. I'm still just laying the groundwork for it. Newton's first law says an object at rest will stay at rest, and more importantly, an object in motion will continue in a straight line unless a force causes it to change. So if something is curving, that's not a straight line. There must be a force that exists to make this sling go round and round and round and round and round like this. So turning is an acceleration, and acceleration needs force. What direction is that force, though? If you twirl your keys, let's see, here's a key, okay, on the end of a string, and that's going around in a circle, like that, there is a force present. There has to be because it's turning. But what direction is that force? It can't be down. That doesn't make any sense because we're not accelerating downwards. And any direction that I chose, say this way or this way, would only be true for a little bit because the key keeps moving. But there is a direction to this force. It's consistent. The force is going inwards towards the center of that circle. If you've got your key going around in a circle, then the force is towards the inside. The key is traveling around and around. It's always turning. And no matter where that key is, that force is an inside pointing force. If you drive your car around a curve, what's the direction of the force? Same thing. Here's the curve, and your car is putting along, going through the curve. There we go. Driving along in this direction. What direction is the force? The force is towards the inside of the curve. Always, 100% of the time, because that's why you're turning. You're turning as an acceleration, and a force has to cause that. So here we go. Number 6, what you've all been waiting for. Centripetal force means center-seeking force. It goes towards the middle of a circular path. Pause it here if you need to write that down, because that's really important. The word centripetal means center-seeking, and it is always towards the middle. If you see the word centripetal force, you know there's a circle and something's pointing to the middle of that circle. Inward force is necessary for any object that is curving all the time. That's our centripetal force that we talked about earlier, the inward pointing force. If you look at these figure skaters right here, they spin around really, really fast. Both of them, but they stay in the middle of the rink. And here's why. This is roughly the center because his arm is extended way on over here. There's his arm. This person's spinning around in a circle, and so is he spinning around in a circle, but at all times her force is pointed towards the center, and his force is pointed towards the center. So they end up canceling out, and they don't actually go anywhere. Inward acceleration. If we have an inward force, that's the centripetal force. Force is tied to acceleration. That's Newton's second law. So if there's an inward force, there's always an inward acceleration. Just like centripetal forces are always pointing towards the middle, that means there's always a centripetal acceleration pointing towards the middle at the same time. Because F and A always go together. So if there's a bucket and you're swinging it, by the way, feel free to pause this at any time. I know I'm going a little bit fast, but I'm trying to keep it from being too boring. If there's a bucket full of water and you're swinging that bucket, the water all stays in the base of the bucket. Why doesn't it fall out? The string provides a tension towards the inside. So if we've got a string, there's our water in the bucket, beautifully drawn. This string provides our tension. There's our centripetal force. Remember, centripetal is always towards the middle. So there's a centripetal force going into the middle. Where's the inertia going in this case? Inertia is always going the opposite way of force because it's resisting acceleration. So force is going inwards, inertia is going outwards. That's why the water stays in the base of the bucket. There was a problem on our last review sheet where there was a hovercraft that was zooming along the swamp or something like that, and it speeds up, and an ice chest on it then slides backwards. And it was because the inertia of the ice chest resists the acceleration. Same thing, if we have an inwards acceleration, then we're going to have an outwards inertia, keeping everything in place. So it's the inertia of the water that keeps things moving in one direction. What you want to do is pause this right now and draw a quick diagram in your notes. I'm not sure what number it is, but it's right after this section with the water bucket going in a circle. It's not a free body diagram, but I want you to draw a picture of that bucket moving in a curve and have two arrows on it. You want to have one arrow symbolizing centripetal force and one arrow symbolizing inertia. Pause it here and draw it. Then press play again and you'll see what the right answer should be. Okay, so we're back. There's our bucket. There's the water in it. Beautiful art. There's the string, and it's going in a curving circle like this. So the arrows that I have, here is my centripetal force, or FC, which means here is my inertia, pointing out opposing centripetal force. It always works that way. This slide is actually an animation that's on the PowerPoint. We'll talk about this when I get back. As a car goes around a curve, the exact same thing happens. The car goes around a turn, zoom in that direction. The friction on the road, which you see right here, is what provides our centripetal force. It's towards the center. That's what's making the car turn. It's turning towards the direction of the acceleration caused by the centripetal force. Now, you get thrown against the outside of the car whenever you turn through a curve. That's your inertia, going in the opposite direction of that acceleration. So again, pause this and draw a diagram of the car moving in a circle, or moving through a curve, doesn't have to be a complete circle, just like before, and then unpause it and you can see the answer. Okay, here we go. Here's the car. Yeah, it looks like a blob, but it's hard to draw in this program, so just lay off. It's going through a curve like that. We've got two forces, or two arrows rather, one force. There's the centripetal force, and there's the inertia, opposing the centripetal force, throwing your body to the outside of the car as you turn. We will talk about this next time, but suffice it to say, this is what I want you to know. Sometimes you'll hear the word centrifugal. No, not right. Centripetal or centripetal is the correct way to say it. Yeah, that's right. A video called Wall of Death. You'll see it when I get back. It's pretty cool. When the moon goes around the Earth, the exact same thing happens. It doesn't matter that it's big and it's up in space, it's still going in a circle. So gravity provides us with the centripetal force that we need towards the inside. Now, why doesn't the moon crash into the Earth? After all, we've got all this gravity going on. Same reason you go to the outside of your car when you turn. Same reason the water doesn't leave the bucket. Because if centripetal force goes in, inertia resists that acceleration, which keeps the moon in orbit. Now, here we've got a old Scottish version of the hammer throw at a Highland Games. That ball right there weighs about 30 or 40 pounds. He's trying to throw it as far as he can. He's swinging it in a circle or an oval for a while right here. Inward force is supplied by tension along this string, this pole right here, this dowel. What happens if the inward force stops? What if that's going to break? Would this ball continue curving? No, it's not going to continue curving at all. The reason we know that is if this stick here breaks and there's no more inward force, then there's nothing to make that ball turn towards this side. Now, it's also not going to fly off in this direction because the only reason we have inertia is because it's opposing centripetal force. So if there's no centripetal force, there's also no inertia. What happens is the object flies off tangent to the circular path. That means it goes off in this direction. That's kind of the direction it was going anyway at that point in the circle. So if there's no inwards force and there's no outwards inertia, it's going to keep on going in the direction it was going. That's Newton's first law, right? An object in motion tends to continue in motion until you act on it. So what does this word tangent mean? Some of you guys know already. It's a line that touches a circle at just one point, but does not intersect it. So this is not a tangent line because it intersects there and there. A tangent line would go through and just touch the wall of the circle and keep on going. That's what the word tangent means. We're not going to do any math with tangent. We're not going to use a tangent function on your calculator. We're just going to treat it as an adjective describing what this line is doing. This can give us artificial gravity in space. It's super cool. I'll show you the video when I get back. Same way, you might be able to figure this out, probably not without the video and the explanation. So feel free to leave some of these blank right there. And that's it. You should have gone through number 22. This one goes a little further. We haven't gotten to this one yet. So, if you've got all your answers for 1 through 22, fantastic, record them. If not, rewind this and work with your neighbor to make sure you've got what you need. And I will check it and see you guys again on Wednesday.